scavengers on all instruments, meaning in the biomolecular facility and in the small molecule facility. Now, some of you might wonder, is that the best thing to do? And we actually did have a lot of pushback initially, particularly in the small molecule facility. Because PIs were like, oh, people need to learn how to run their experiments. They can't just put in the sample and program it and there we go. So we did have all that pushback, but it turns out that as time has evolved, the instrumentation is really improved as well and gives great results in automation. And in the end, people really, particularly in the small molecule facility, need to focus on the results. They need to use the NMR as a tool. They don't need to be experts. And so that's why they're using it. Now, it's a little bit of a different story in the biomolecular facility. There, we still do manual setups, mostly, because we have to tweak out the last little signal that we can. We still have sample jets and sample cases there because we do the IVDR mass experiments, screening. We set up mass number of samples and just screen one after the other, and that's what we're using them for. We do have cryoprobes on 3 instruments. We actually have them for 5, but IVDR and the small molecule don't really use them, so we save the cost of maintaining them by shutting them down, and we have them now at the 3 instruments, 6, 8, and 900. Nitrogen separators and UPSs are standard on all the instruments in the biomolecular facility. We have pump stations for the 8 and the 900. And we do have a facility backup generator for the 8 and 900 because they need to run 24/7 with the pump stations. We share some of the instrumentation with the small molecule facility, like the medical air compressor, and we do also have a shared helium liquefier. The 2 facilities are close enough together that we can combine it and utilize it for both, which actually is a great cost savings. So this session is called Structural Biology Course, Opportunities and Challenges. And we are part of the Center for Structural Biology. Now, how much structural biology do we actually do in the NMR facility? I can tell you not as much anymore. There has been a big shift from the 90s to the 2020s where really structural biology is not the focus anymore. So we're not doing many structures, but what we can see is we have shifted a lot into chemical biology and analytics. That's really where we're going, and if we look at the strength, we really have our strength that we can work in the physiological environment, in solution, and that's really one of the big advantages that we have in NMR for drug screening, membrane proteins that often use the mimics, metabolomics, we can even do in vivo or in-cell NMR. So those are the things we need to focus on. We also have a strength that actually reaches over to other methods where we can easily detect the folding of a protein in a native state or in a mutated state. So normally we have this nice spectrum where the peaks are really nicely spread out, but if we have a mutation or if we have folding issues, our spectrum very rapidly can tell us that this is the case. And we actually have had some X-ray people come over. They've been trying to crystallize for months, and we're like, well, what's going on? And we ran the spectrum and told them, oh, it might be partially destabilized or heterogeneous, and that's why you cannot fold it. So that's where we have another advantage. Binding interfaces, that's our drug screening, where we do a lot of that. Or we look at protein-protein interactions, where each of these peaks in the spectrum is an individual sensor in the protein, and we can then easily find out where are binding interfaces, where is binding happening, and even quantize it by getting a KD. We can look at internal motions, which is kind of a neat thing in NMR. And then, as I said, analytics really has become more and more important for the screening for biologics, particularly in pharmacy, where they test their biologics for proper folding, for impurities, and they use NMR to quick run these big molecules, proteins, to see what they do. We do quantitative NMR, which also is part of the metabolomics, which we utilize the quantitative aspect of NMR quite a bit. So we have many, many advantages that we can use in NMR. But we also have some limitations that make it sometimes hard. NMR is clearly an insensitive method. So to improve the sensitivity, we often need either higher concentrations, we need higher magnets. Bigger magnets, higher fields are very expensive these days. So if you go to a 1.2 gig, easily talk about 15, 20 millions, which is unaffordable. Another way of getting more sensitivity is cryogenically cooled probes, and that's what we have on the 6 through 900. They give us a real strong boost in sensitivity. Or we can do smaller things like deal with sample diameters or oxygen-free samples that help us with the sensitivity. Resolution, another issue that we are limited by and are a little more troubled than other techniques. 45, 50 kilodalton proteins are probably about the max that we can easily do. If we go to bigger systems, we have to selective label. Resolution also would benefit from higher fields, same like the sensitivity. We do have these days more options in acquisition and processing techniques that we can apply to increase the resolution. So there are some tricks that we can use to address this issue. And then quite often, another limitation is the sample. People sometimes come to us with the idea of some other analytical methods that need micrograms. And we're like, not so easy. So we do need a decent amount of sample concentration. Some other limitations are salts, detergents, and stuff like this that can interact and give us some problems. So we do have a few limitations that we need to deal with in the method, but we also have some challenges that we need to deal with, and we have had a whole session yesterday afternoon about training, and it resonated greatly with me because some of the things that were discussed yesterday are actually very true in our facility too. We have students that come with completely different backgrounds. We have postdocs, graduate students, undergrads. They obviously are in a completely different state of education and have different knowledge. Then on top of that, we have people that have worked with different vendors, different machines. So they use different software. They came out of different labs that had different modes of operations. So there is a whole range of different backgrounds that we have to deal with. We address them normally by forcing or asking the new students to attend a workshop where we really go through, first of all, administratively, how we are set up, how can you access our facility, but then also go and explain them how they can measure a spectrum easily. So it's kind of an introduction that helps them to really utilize the instrumentation. There are also credit classes that we offer at Vanderbilt that they can take to get their theoretical knowledge, because these workshops really focus on the practical aspects. Usually that's not enough. A lot of the small molecule users, if they use automation, that might be fine. They might be good to go. But particularly people in the biomolecular facility, they often need more hands-on experience. And so what we then have to do is we have to help them. Often they come with projects that they do maybe once in their PhD, like a whole backbone assignment suite. What do you do with them? We basically are of the opinion it's really not worth to train them so they can do it on their own. So what we then say in these cases is, let's sit together, set it up together, and then we'll show you how you can analyze the data. Or then there are people that see something in the literature, an experiment that would be good for them. They come to us and say, hey, can we do that here too? And that's when we have the one-on-one sessions and try to figure out how we can set up these experiments. So those are challenges with the users. We have also challenges in terms of administration, particularly regarding cost. And I separated between regular costs and irregular expenses. How do we justify and fund new instrumentation and upgrades? A huge issue because NMRs, like other methods, are pretty expensive. So there are federal funding sources that we try and try and try, and sometimes we are successful. But it can be challenging. And the regular sources, they often have limits in the 2 to 4 million range. So if you need an instrument that's 10 to 20 millions, you need to find other sources. And there are federal programs that would allow that, but those are more than for consortia. So you need to build a regional consortia to actually get that going. Another big issue is how do we recover the cost? There is a depreciation model, but if you want to depreciate an instrument that's 5-6 millions over 10 to 20 years, the user fees go through the roof, and it's impossible. So we can't really do that in many cases. So we do rely a lot on internal funding, some philanthropy, private sector, which is not always easy to get. So those are these costs, and then we have the irregular costs. Our spectrometer has a magnet, it has the cryo platform, the console, that all need to be maintained, and in our case we do have a helium liquefier that also requires maintenance. So I've put down some estimates of costs when, that we incur, and you see here one of the big problems is these costs are variable. Some are every 6 to 10 years, some are every year or every other year. So how do you budget them? And as you can tell, some of these costs are substantial. And if you have multiple instruments, they multiply. They're just not just the 20,000 or 25,000, but they might be 3 times 25,000. So the budgeting problem can be a real challenge. The goal for me to budget is always to have an as stable as possible user fee in the long run. Because the PIs need to count on us having stable fees. They need to put that into their grants, and we can't just 1 year, because we have these irregular costs big, jump the rates up and then the next year put them back down half of it. That just is not practical. But we have a little bit of a budgeting conundrum, because as a core, we are supposed to be balanced on a yearly budget. So that is directly against some of these large irregular fees and maintenance items or unexpected repairs that we encounter. Last but not least, we also deal with a variation in usage. There is times when everybody wants to run a spectrum. and then they disappear for half a year or a year because they're writing a paper, they're analyzing their data, they're working on their dissertation. You don't see them. So the usage can vary quite a bit. So that is a true challenge. How do we budget when we have to balance the expense versus cost in the income at the end of the year? It's not an easy task. So given these opportunities and challenges, is NMR here to stay? Is it really? The good news is I found this little graph, this model that predicts that over the next 5-6 years, the annual rise in expense for NMR instrumentation is predicted to be about 5%, driven by academia and pharma, both of them, surprisingly. So this model will predict, yes, we are here to stay. But I think there is a couple of things that might change. We'll integrate with other methods more often. AI support will actually impact drug discovery. NMR probably will stay pretty strong for small proteins, IDPs, and membrane proteins. In vivo NMR will be here. Personalized medicine will have a pretty strong point in that area. But the other thing that might actually change is that facility models may change. We may have to consolidate. Like in our case, we may not be able to afford having 2 dedicated facilities and may have to combine them to have a synergistic effect. So things probably will change, but I do think, given the advantages, the opportunities we have, I think NMR is going to be here to stay. Just to summarize it up, we have opportunities that we mentioned, and we have challenges that we need to overcome on a daily basis or yearly basis. And that's where I'm curious to hear what you all have to say about it. I have some ideas, but I want to leave it open for question and answers. I really appreciate you being here, listening to this, and I'm curious what you have to say.